And then really, the rest of this unit is us learning the rest of the derivatives that you will be encountering in calculus. And by the end of this unit, you'll just be able to differentiate any function that comes at you. Anything at all. Yeah, I always. All right, so this is the challenge. We're going to take the derivative of 3x plus 7 squared. And I'll just show you what you would have had to do up until today if you didn't have a chain rule in your life. And that would be this, which is not, for this problem, in fact, it's actually doable. This is not bad at all to do this with this particular problem. Do you agree that that's what you would have done? You know?
Yeah.
Wait, why is it y double?
Oh, sorry, y prime. All right, the new way is I'm going to show you what this is first, and then we'll say why this works in a minute here. We're going to differentiate this. And actually, this kind of relates to on Wednesday. I was talking when we went over the AP problem on Wednesday with our few minutes together that we had. And do you remember it gave you some derivatives at the top? And then we just kind of had to hand those to you because we hadn't learned the chain rule yet. So I think there's a real strong temptation to just do the power rule, right? Just drop the 2. And actually, what we're going to tell you today is like that's actually permitted. Provided, so if you just ignored the inside, like what's the, what is that for people in the front row?
Monkey.
Yeah, it's a monkey doing this. All right. So if you ignore what's in the middle there, and you just took the derivative of this as if it was like monkey squared, you'd be like, well, it's just 2 monkey, right?
Yeah.
Right? Just go with it. Okay. No, but of course that's not correct. In fact, you know that that's not correct because that is not this. That is not this. Right? Y prime is 18x plus 42. It's not 2 times 3x plus 7. Right?
Yeah.
So the penalty, and we'll tell you, again, we'll give you more theory behind this in a second, but your penalty for being so cavalier, ignoring the inside, is that you just, it's not actually a huge penalty. You just have to afterwards multiply by the derivative of the inside that you ignored. So what is the derivative of the inside? What's the derivative of the inside part? 3. So you multiply by 3 at the end, and then you do get the desired result. Notice that that is, if you actually multiply it out, the same thing as what we got. Okay? This is your first. So this is me showing you how the chain rule works, and then I'm actually going to write it in a box on the board. And before I do, maybe you can tell me what you think it should say. The chain rule deals with what kind of situation are we in? If before, when we were taking the derivative of f times g, we were dealing with a product, or when we were dealing with derivative of f over g, we were dealing with a quotient. What situation are we in now? What are we trying to take the derivative of, Michelle?
Like a composite?
Yeah, we're taking the derivative of a composition of 2 functions, f of g, yes? That is when you're in that situation, f of g of x. You're in a chain rule situation. All right, so if this is f of g of x, say, what did we do down here? Can you express it in terms of f primes and g primes and f's of g and g, right? Can you use that kind of composition language to describe what we just did? Go ahead, Franklin.
Normally you would add that twice.
Well, no, I'd like you to express it in the language of compositions because in a minute we won't be able to express this as a product. You're right, you could do this as a product rule too. You're right. This particular problem. Yeah, Caduce. There's definitely an f prime involved somewhere. That would be like the outside function. The derivative of the outside function. We did do that, didn't we? There's definitely an f prime. Katya, help us out.
Well, I kind of separated it into like f of x plus x squared and g of x plus 3x plus 7.
Yeah, I like that.
That would be the derivative of f of x times g of x times the derivative.
Close. Here, let me do one more for you here too. Do I have it on the next slide? Yeah, here. Let's do one more here. So how would this one go? And then we'll see if we can generalize a little better. give it a try using the chain rule. You can see already it's not desirable to do it the old way on this one maybe, right? So what do we do? Take the derivative of the whole thing as if it's like something cubed. What's the derivative of something cubed? 3 times that something squared. So just start by just writing that down. And then what's the penalty afterward? Yeah, multiplied by the derivative of the inside. So we're just ignoring this, right? What's the derivative of something cubed? It's 3 times that thing squared. Oh wait, afterward, multiplied by 4. Okay. You could certainly clean it up afterward too if you want a little bit, but huh? So you take the derivative of the outside function. It's just 3 times the thing squared, just like it, and then times 4, which is the derivative of the inside. All right, someone willing to say it again? What do you think the generalization? I'm going to put it up here in a second. You know, it's going to come up, but I want to see if you can scoop me on it. If this is f of g of x, I want to know what is the derivative of f of g of x. Cameron wants to try.
Is it f prime of g of x times g prime?
Say it one more time. F prime.
F prime of g of x times g prime.
Do you agree with that, Michelle?
Well, I often say like f of g of x prime times g prime, but I don't know if there's a difference.
F of, say it again.
F of g of x, like f of g of x prime times like g prime.
Yeah, okay. Yeah, I think that's okay. If you're thinking of taking the derivative of f and then inserting g.
Yeah.
Yeah.
Okay.
And then afterward multiplying by the derivative of g.
Yeah.
Yeah, I guess I don't need to put an equals here. What Camber said, I think what Michelle said too, is correct. Yeah. Just verify those who had other suggestions that this is really what we mean, isn't it? So we take the derivative of the outside function, in some ways, like I said, disregarding whatever complexity there is for the inside function. We just have the inside function kind of coming along for the ride. And then afterward, you're multiplying by g prime. I will say that this is at play all the time, and from now on, you don't know how this is always going to be with you, but I just, because you haven't experienced this unit and the rest of this course. But you just need to know that the chain rule is like 100% of the time at play, all the time. Very easy to forget the chain rule, but it's always there. Even on something as simple as taking the derivative of 2x, of x squared, which is something you've done before. Technically, the chain rule is at play there too. It's just we didn't really talk about it. Do you see why? It's just the inside function was x, and its derivative was 1. So it's always been there, lurking. All right, let's try a few. I let that one slide. I decided that would be okay for there to be a dagger there.
Why is there a dagger?
It's a dagger.
How does that relate?
Because it's hard and it's like treacherous. You need to be careful is what that means. It's really, yeah. All right, so what's the derivative of sine of something? That's right, it's cosine of something, right? Just stick. So f prime of g of x. You just put g of x in there. And then afterward, multiply by, got to fix our situation, because that was a little bit, like I said, cavalier. So yeah, just have to multiply by the derivative of the inside. And notice again that there is just no other way to approach this problem except by using this rule. It's not like you could have also done this using some other technique we've already seen. This is a function that I just could not have asked you to differentiate on the test yesterday. The last ones I could have. not wonderful, Franklin? What's wrong?
I wanted to get printed today, and then like I was.
We're gonna be done soon. Don't worry. Why is there a dagger on the second one, friends? Yeah, what's going on there? I mean, we want to make sure we're clear. The thing we're taking the derivative of is cosine of 3x squared, right? Is it clear that that's the thing we're taking the derivative of? Why is there a dagger? Why is this more interesting, I should say, not harder maybe, but more interesting than the last one? Listen, please. While Amy addresses the question.
You have to do between twice in order to address the squared and the
Yeah, you've got like f of g of h of x or something, right? That's not a problem, right? The chain rule can be applied recursively here, okay? What's the derivative of something squared? Notice, make sure you're really clear about what the inside and outside function is here, right? What's the derivative of something squared? 2 something. I guess we'll just do that. So 2 times that thing. See how easy that was? Oh wait. What's the derivative? Side question. What's the derivative of cosine of 3x? Because we're going to need it in a minute. What's negative sine of x? Oh wait. Sine of 3x. Times 3. Right? Alright, so now we're ready to finalize this question here, right? What's the derivative of this thing squared? Well, it's 2 times that thing times that times the derivative of the inside, which is negative sine 3x. Oh wait, times 3, like we said, right? Do you see how we like kind of have each time the next inside derivative popping out?
Like a chain.
Like, you might even say. A chain, yes. We can clean this up a little bit. Maybe we just say negative 6 cosine 3x sine 3x, right? What do you think? Can we handle the 2 chain rule application? Yeah, you stop before the derivative is 0, right? You could use the double angle formula. The negative 3 sine of 6x. Yeah, good. All right. Whoa, what's going on here? This is the kind of thing AP loves too, right? Give you a bunch of information that you just happen to, or maybe you don't need all of it, that you might happen to need to answer this question without actually knowing any of the functions. So what is this? Remember this simple? What does that mean? Yeah, it means the situation we've been talking about. F of g of 3 prime, f prime of, excuse me. It's the whole thing prime. Right?
You can still just put the prime next to f, right?
No, because that's just the derivative of f with the g plugged in.
Okay.
So what is this? Let's not use, don't look at any of the other stuff. Let's just write down the chain rule. What is the derivative of f of g of 3? It's f prime of g of 3 times g prime of 3 by like the definition of the chain, or the theorem, the chain rule. Yeah. Do we have what we need here now? G of 3 is a thing that's a known quantity. Can you see it? Plug it in. Yeah, so now we have f prime of 7 times g prime of 3. Keep going, keep going. So f prime of 7 times g prime of 3. What's f prime of 7? Was that given? Was that given? Fortunately, g prime of 3 is 5. So what do we get? What was, listen, thanks guys. What was it, what were the distractors in that problem setup? What are the things you didn't need? You didn't need this, right? Is there anything else you didn't need? That was the only one, right? But it's there waiting for the person who thinks they need it. Okay? Don't be that person. Okay. All right. Here's an important, this also shows the power of our notation, I think, too. This is an important, extremely important, I should say, alternate form. And in some ways, I haven't really illuminated why the chain rule even works until now. But now maybe you see now. This is at least, I won't say this is a proof, actually the actual proof of the chain rule we're not going to cover in this course because it's a little bit complicated. And I don't think it's very illuminating. I think this notation itself illuminates the reason, at least on a gut level, why this is working. First of all, does it make sense why symbolically, at least from first appearances, why this kind of makes sense? What is you? What is you? Well, let's do the last, just because this looks, you're so excited about this, right? Because you're like, this looks beautiful, except I'm not sure I quite understand it. I'd like to understand it though, right, is where you're at. Well, let's go back and do this problem that we did before. And do it using this idea. Okay. So dy dx is this, or y of x is this function. We desire the derivative of y with respect to x, eventually. But we can also think of this as being a composition. We're going to let u be our new symbol for the inside function. Okay. And now what do we need in our lives? We need dy du. Well, what is the derivative of y with respect to u? What is this function? It's sine of, in terms of u, this function is sine of u. So what is the derivative of y with respect to u? If y is just sine u, it's just cosine u, right? So dy du is cosine u. What's du dx? That is the derivative of u, this function here, with respect to x. That's just simply what? Isn't du dx 2x? How did he do?
It's just a little slanted. I think it's because I was slanted a little.
15 minutes.
Turn the board. just turn the board.
Right. If we just unscrew the board, we can make it straight, right?
Yeah.
Like this part.
Yeah, the metal frame.
It's because you're.
Actually, no. Why don't we just tilt the tires?
That's the same.
No, then
You're,
Why don't we tilt the tire?
Just tilt the sign on top too.
let's take a vote. Should William fix the calendar?
No.
Yeah.
You should do the entire thing, guys.
All in favor of him changing the calendar, please raise your hand.
Y'all are haters. I don't know who y'all are, but.
I was going to vote yes too, William. Just a little tweak on home, just put a little down just a little hair. You got it. I believe it.
wait. See, all you have to do is take out one.
Yeah, just take one of
Make the one
them.
on the left a little higher.
That's a little too high, yeah. William, I won't make you do this again after this successful attempt. Yeah, he's gonna make it work, I think, but we'll make someone else do it next time who has
Now the October sign is
a
there.
better sense of love. All right. So am I right about dy du in blue here? dy du, do you believe me that it's cosine u? Do you see that there?
Yeah.
If the original function is y equals sine of u, because we said so, right? We just declared x squared minus 4 to be u. Then it must be true that with respect to u, not with respect to x, that dy du is cosine u. It also should be clear from what we let u be, that if someone just asked you, hey, here's a function u equals x squared minus 4, what's du dx? You'd be like 2x, right? I think you all would say that, yes, of course. All right, we're ready. We have the elements we need. What's dy dx? Well, we told you a second ago that this is, in fact, the chain rule. dy du, cosine u is what that is, times du dx, which is 2x. And that's the derivative. Except you might want to say, again, what u is. It's x squared minus 4. Yeah. Do you see why this is equivalent?
Does u only matter in trigonometric settings?
Not at all. This works for any chain rule problem.
But then what's u in a
Yeah, so like go back to one of the problems we did before, like say 2x minus 4 cubed or something, right? What's u?
2x?
Right. Yeah. Let u be 2x minus 4 and run with it, you'll get the same result. Yeah, you'll get the chain rule. So I hope you see again the power of the notation itself to be explanatory, right? In Leibniz notation, it almost kind of, can you see why it almost like just cancels out in some sense? No, you don't like that idea.
No, I just don't like math.
Amber, math likes you.
I only like it as a
Now,
friend.
would you like to talk about parametric functions for a second? I thought you did. All right. We're gonna have a whole unit on this later in the year, but this will play in strongly. And so right now, even we can compute some parametric derivatives as well. Notice here, this is the chain rule again. Except instead of u, I've decided to use the letter t. Is that okay? Don't be scared.
What's the same?
Same chain rules before. It's just with a t instead. So what does that mean? What does that mean? It means that if you want dy dx, that's the same thing as dy dt divided by dx dt. Do you see that, little fraction action? Okay? You got it right? Little divide by, same as multiply by the reciprocal type deal. All I did is do a little fraction magic on the right side. So that suggests a way of calculating the slope, the traditional slope in the plane, y with respect to x, of a parametrically defined curve with functions y of t and x of t. What do you do? What does this even just suggest from its form? What are you going to do when I hand you a function y of t equals this, and x of t equals this? Well, what does this call for? You're just going to take the derivative of y, that y function, with respect to t, and then the derivative of x with respect to t. Stack them and call it a day. So, for example, this is, by the way, this is an ellipse here. We've got 3x is a function of t, 3 cosine t, and y is a function of t, 2 sine t. Take the derivative. What's dy dx? Then, in terms of t, this is dy dt. I just want you to take a derivative of each of these, and dx dt, just with respect to t. What is the derivative of this with respect to t? Negative 3 sine t. Then what's the derivative of this with respect to t? 2 cosine t. Done. We're done. No, we're not done. We're done with that problem though. Yeah, that's it, right? Let's just check a few.
I'll take your word for it.
It looks kind of fancy.
What?
Yeah, you should go back.
I think it's a little too close to this.
The one on the far left is
It needs to
slanted.
move
Yeah,
off.
check.
The column on the far left is still slanted.
Move everything like half an inch right. No, actually, it's just the angle.
All right. So let's just try this out and make sure it makes sense for us too. Now keep in mind t here. Let's treat t as being an angle, right? Just because we're taking cosine and the sines of it. So if t is 0, well, let's start with t equals pi over 2. What if you plug pi over 2 into the original equations? Notice that you get the point what here? If you plug pi over 2 in here, what's cosine of pi over 2?
0.
So you get x equals 0. And in the original functions here, if you plug in pi over 2 to y, you get times 2 is 2. So you get the point 0, 2 if t is pi over 2. So that does place you right here. Yeah?
Yeah.
All right, but then what does this say about where we are? If t is pi over 2, what is the derivative telling us? We get pi over 2 here and pi over 2 here. So what is that? Cosine of pi over 2 is 0. So we get 0, which is what you would want it to say, right? What about down here at 0? If t is 0 degree, 0 radians, what do we get there? What slope do we get? We get undefined. Is that the slope you would want to say about that, the tangent line to this curve there? Absolutely it is. The tangent line here is definitely vertical. And you can try another one. Let's try one more. How about pi over 4? Or something. Pi over 4, what do we get there? In both cases, yeah, what is that going to come out to be then? Just this side, cosine t over sine t. Since they're the same, what do we get? Negative 2/3. What do you think? Could I convince you that the slope at pi over 4 is negative 2/3? Yes. I think I could convince you of that. All right, so I just want to make sure you're clear on how that can work for us. A little parametric action there. Let's do one more. This might last.
It's the one where it goes like it goes up and then it goes down. It's a straight parabola. Yeah, and then there's like it's like a cross, right? And then there it goes up and then it goes down.
So this is just one branch.
Yeah. So like remember there's like the aspect on both sides and then on each side there's
You don't actually have to know anything about hyperbolas to solve this problem. Just run the calculus and call it a day, okay?
Was that algebra 2?
It was like algebra 2.
Algebra 2, conics, I guess, or geometry. We would have encountered the parametric forms for those a little bit in pre-calc then too. It's not important.
I have an organized anarchy. Unorganized anarchy.
I don't know what I can
The opposite of organized anarchy is
Did I need to tell you at the point root 2 comma 1? Did I need to tell you that? You could have found that using pi over 4, right? You could have found the point, but I did.
Pi over 4, which is in the range.
organized, absolutely.
All right. Jack, if you could help me out here, give me the derivative. Go ahead. In terms of t. In terms of t. What is it? What's the derivative of tan t with respect to t?
But this squared, so it goes on the outside, right? No, never.
How about just secant squared? Go. You do the bottom now.
Secant x and t tan t.
Good. And that actually simplifies a little bit. We can, what do we can say here? Sec t over tan t. But those are, let's see, that's 1 over cosine over sine over cosine. So that's 1 over sine. Yeah, so this is 1 over cosine and this is sine over cosine, so the cosines cancel, right? Alright, so that actually works out nicely. We're not done though. It says find the equation of the tangent line, right? So at this point, so when t is pi over 4, what do we get? So dy dx at t equals pi over 4. When you plug pi over 4 in, that what do you get? Root 2 over 2, but then...
I meant just the regular, just without the over 2. Ignore the second part of that.
Yeah, just root 2. Yeah. Good. Yeah, just root 2. Yep. All right, so I think we're ready to write the tangent line here. What is it? Y equals 1 plus, what's the slope? root 2 times x minus root 2, right?
I understand.
Right?
That's
Yeah.
right. That's definitely right, guys.
Is this too hard? There are a couple like this on the homework.
I'm not glad.
Generally speaking, no, this is not what the homework is. Mainly the other problems. But there are a
I
couple like
think I
this.
get it, but like, I'm gonna need a lot of practice.
Yeah, you will need to practice with the chain rule. That's for sure. For sure, for sure. You know. So we're gonna get How did he do in the end? How did William do in the end? Did he do a good job? What do you think?
To the left. Too far left.